Yes. Yeah. Driver Z just one.
Oh, Z. Yeah, it's four meters in the swamp.
Yeah,
Therefore, it's right.
uh-huh.
But in parentheses,
So last week we have been talking about the transformer. We start a little bit and then we try to continue. So last week we talked about briefly about the transformer history. So that's quite straightforward. Just give you some information. And then we also mentioned about the high frequency transformer. Why we like to have high frequency? Because high frequency mainly able to reduce the overall size of the components. So that's something we like to have. But as high frequencies, we should use the power device, which also can be high frequencies, which is like the MOSFET, this item. One thing you can see that we mentioned about the energy equal to half Li squared. That's the energy equation, and if you go to power equal to energy multiplied the frequency. So that means in this case, this whole expression becomes I square F. So that is to say, if you go for a very high frequency, we can actually reduce the inductor size much smaller in a proportional manner. So that's why when you go for high frequency transformer, we're able to reduce the overall size of the transformer because we reduce the transformer inductance. So that's the concept why we need to do that. And then we also mentioned about advantage, disadvantage. And then we also have the equation for the reluctance. Basically, reluctance equation are very similar to the resistor, which relate to the length, relate inversely proportional to the area, and also relate to the permeability. Permeability is a physical parameter. For different parameter for the material, then we can usually mention about the relative permeability. Yeah. But you can see that for any magnetic core in here, like this iron core, sometimes we add an air gap in order to increase or control the total reluctance. So that to say, if it's reluctant in this path, we also add reluctant in here, the total reluctance summation. So the flux, which is so-called the flow component. So the flux here is the flow component. We flow through something, and then Ni is the source, which we call it MF, right? Metromotive force, which is we mentioned here. So that's how we get that. So once we get the flux, the flow component, the density, which is the flux density, is just divided by the area. So in this expression, we usually assume the area could be really much equal. Why is that? Because even though we could have some fringe field here, the fringe field can increase the total area. So the area due to the air gap. So this area could be larger, but however, when we decrease the air gap, then this kind of the fringe field area will be minimum close to the geometry area of the magnetic core. So that's why in here, we just assume these two are equal, make our calculation is simple. So that's why I can see that the B field of these two are very much similar or equal to each other. So that's initial assumption. That's the most common assumption we use in the pedicle transformer. So this example shows us about the relay. We also mentioned last time, assume we got the number of turns will be 500 in here, and the total core length will be this one, will be 0.36 meter. The air gap will be 1.5. So because we got two air gap in this loop, total air gap will be multiplied by 2 anyway. And then the B field need to actuate the relay in here. The typo here, that should be the relay, right? Calculate the current and calculate the permeability and the relative permeability of the core. So usually the magnetic core, we don't need to say the permeability. We usually say about the relative permeability. Relative permeability, the symbol is called mu r, right? Permeability, we call it mu. So as you know that all the permeability equal to mu log and mu r. Mu r is the relative. I think you learned them in physics, right? So that's how we get. And then when the relay is closed, then because we reduce the air gap in here, so actual of the current requirement or MMF, the force requirement will be lower. So that's how the question asking us about. So now then in the calculation, we are given with the requirement of the B field density, which is 0.8 Tesla. T is the unit for Tesla. I think you all know that. And then H field will be 510 ampere per meter. So you can see that the unit here is the T. T is the turn. I also mentioned here last time, turn. You see turn have no unit. It's not a unit anyway. It's not SI unit. So just for clarity, people put AT per meter, but some people just using A per meter also good enough because turn is not a unit anyway. So either way will do. So now then we need to calculate MMF, the driving force for the relay, for the coil. So which is the H field intensity multiplied the length, which is 510 multiplied by the magnetic length, which is, you can see here, magnetic length, which is give us this requirement for the H field to drive the relay. So just look like the input voltage. But here we don't say input voltage for magnetic circuitry, we call it the MMF, driving force, electromotive force. So remember this name, MMF. So that's a really important parameter we use. I think last week we also mentioned that's a table compared to magnetic circuit and electrical circuit. So that's how we relate them. So just remind you, MMF relate to the voltage, right? And in here, the flux relate to the current, I. And then reluctance relate to the resistance, right? So that's how the relationship. Do remember that circuitry. We'll go for a number of examples. Have you all learned the magnetic circuit in the past? In physics? Have you learned them?
No.
No. Okay, that's okay. It's very simple Ohm's law, so I don't think you have any problem. I will go through them, go through my example. Anyway, so that means total force requirement just look like summation of the voltage. So these two add together. This from the magnetic core, this from the air gap. So total driving force MM is this one. So we need that driving force from the input system, the coil. So that means we divide number of turns because the MMF also another equation is the N number of turns multiplied by current. So we divide the number of turns, give us 4.19 ampere. So that's the current requirement from the coil. So you can see in this diagram, we just input 4 M in here, 4.1 M in here, with 500 turns here. Will give us this requirement of the MMF to drive the system. This is how we calculate. So apparently you can see that most of the force appear in the air gap. Do you get that air gap? That's really similar to the electrical circuitry potential divider. When you have a large resistance, then all the potential will mostly go to the high resistance. So similarly here. So that's why you can see here, there's a lot of similarity between the magnetic and electric. So you can see this comparison. So next question you ask about the permeability of the core. So the B over H is the permeability. That's a really basic equation for electromagnetics. So that means we now have 0.8, which is Tesla, divided by 510 of the H field intensity. Then we just give it the permeability. The permeability is difficult to memorize because it relates to a quite small number. So we usually divide by the free space mu naught. to give us the relative permeability. Just now, I showed you all the permeability actually equal to mu naught, mu r. We mentioned about, we try to describe any material by the mu naught anyway. So we get the mu naught. So if you say my magnetic core is 1250 permeability, that is more reasonable, easier to remember. For instance, pure air is 1 iron, it will be something like a few thousand. So that's common. And so part C will be, if the air gap becomes 0, that means when the relay coupled tightly with the air gap, then, so that's to say in here, if the air gap becomes 0, that means this already actually, these two are close to each other, closed circuit. Then in this case, air gap becomes 0. So then the original equation in here, this becomes 0 because then we only have the 184. So 184 we divide by number of turns becomes 0.36 M. So that means once the circuit becomes closed, the current becomes much smaller because we don't need additional energy power to drive the air gap. So that's how the phenomenon for this kind of simple machine for a relay. Well, we explained to this question last week, so just go through briefly so that you understand. So, and then we also, next section about the inductance. Induction, I think we all know that one of the major equations we call the flux linkage. That means flux linkage, this term is mean the flux, the flow component, fluid component. You see, we got the flow component here. Anything we got flux pass through, and we've got a different kind of turn here and turn. The flux linkage means how the flux are linking the number of turns. So more linkage, you got more MMF, more driving force. So that's why this kind of the flux linkage mainly relate to us how the flux begin linking to magnetic circuitry. So flux linkage is really basic term for electromagnetic, just mean how the flux are linked to a number of turns in a closed system. So the inductance, because we have many coils here, so the definition, really basic definition for the inductance is the flux linkage per unit current. So that's basic equation, really fundamental equation. Although the equation you learn may be in this one, is the how we relate geometrical shape parameter, but the basic equation is this one. So if we substitute the BV equation or the BH relationship into this equation, then we can eventually get to the inductance equation, which is also really famous equation, which you can see that most of the inductance coil relate to the number of turns squared, n squared, proportional to the area of the coil and inversely proportional to the length of the coil. Of course, proportional to the permeability, usually proportional to mu. So if we went to the equation, we found that it's equal to n squared over reluctance. So that is to say most of the inductor, they usually proportional to n squared. Really common. 99% of inductor are proportional to n squared. And then inversely proportional to reluctance. Reluctance just more look like the resistance, right? But magnetic resistance called reluctance. So that's the equation. So that's common definition you can see in most of the textbook or internet. So this simple example shows us how to do some basic calculation, including if now we got a core. Core length will be 50 centimeter. We do have some air gap in here, will be 1 mm. We do it. Hello?
Does the air gap area refer to like the area on the exterior of the core?
No, the air gap area. So you see if we got any magnetic core, like if in here, then we got some air gap, right?
Yeah.
Air gap is something we tend to put some resistance to the magnetic circuitry.
Yeah.
We don't need to put air gap. However, the air gap, we can produce some resistance. We control the magnetic flux. You see the magnetic flux just like a battery, we connect a resistor. If you want to control the resistance, control the current, then you need to adjust the resistance.
That would be the.
But once the magnetic core is different core, like different resistance, you cannot adjust the current pass through. The magnetic circuitry again, if this circuitry, then if you want to control the magnetic flux pass through the circuitry or control the amount of energy stored, then you can't do much about it. But using air gap, you can control it. You can also adjust the air gap. Air gap is what you can control quite easily. But putting a magnetic core, once you make up or construct magnetic core, you can't do much about it. It just look at additional parameters. You can do it. And also there's another advantage. Now you can control the medical won't be easy get saturation. So later on we discuss about saturation, and we don't like saturation because it can make the inductance become less inductance. We don't like it. So that means, so in the calculation or in the design, we usually allow some air gap. You see in a motor, between stator and rotor, we cannot have physical connection, crash, right? Collision, we don't like that. So that's why there is air gap between the stator and rotor. So this is air gap. So now then I introduce to you some calculation air gap so that you know how to understand the reluctant air gap, magnetic flux, and B field. Prepare for your next chapter for the motor. Okay, get that? Everything has some air gap, no matter small or large. But usually air gap in motor will be quite large, quite small, about 1 mm. But anyway, you say if air gap 1 mm, the cross-sectional area for the air gap is 15 centimeter. And again, we assume a simple calculation, air gap area, same as the core area. The permeability for the core will be 3,000. A few thousand for μr is quite common for metal core, very common numbers. And then the driving current here, 1 amp, the number of turns is 400. So we are asked to calculate the flux in here, and also flux density, like the B field, and also inductance. So in typical equation, now we calculate the core reluctance, that means the resistance. The core reluctance are basically from the physical parameter, from the geometry, from the length, from the area, and permeability. So we lump all the components into here, then we get the reluctance. And the air gap reluctance, we can also calculate by the air gap length 1 mm in here. Mu naught, I think is universal constant. You all know that 4 pi times 10 to the -7, and then air gap area, we can get the air gap reluctance. The total reluctance summation, the driving force is N times I, number of turns times current. So that gives us the full component, the 0.64 Weber. The flux unit is called Weber. Weber is also a famous scientist. The full name is this one, but SI unit, we're just using WB. Yeah. Again, the reluctance here is optional. You don't need to put T because T is without N unit. Just put it here for your better understanding. So the density, the B in magnetic flux density is the flux divided by area. So we know the flux value divided by the area, it gives us the density, right? So next is asked about the inductance. Inductance coil again is the N squared divided by the total reluctance, the basic equation, right? So N is 400 divided by the 2 reluctance here will give you the inductance. As I mentioned, inductance usually the unit more look like mini H. Because the H is really large parameter. So we use the inductance using mini H will be good enough. Or reluctance, so inductance you can calculate by the flux linkage divided by the current. Flux linkage N times the flux here, and then divided by the current 1 also give the same parameter. This was the same equation anyway. All right, so that gives you some kind of the really basic manipulation for the B field, H field, reluctance, and also inductance, and how to mix with the air gap in a core. So they're really basic parameter. If you go to any website, any internet, you can search many of these examples. In my end of my PPT, I also show you some link which you can see some kind of the internet, how you understand more about it. Any textbook will mention this. So here we will be another coil, toroidal coil, just like this one. So again, we got a number of turn total, number of turn 250. The inner outer diameter will be 20 centimeter and 25 centimeter air gap. We do have some air gap in here, assume 1 mm. So the relative permeability can be obtained from the BH curve. Later on, I'll show you a BH curve. Here, example, show you the mu r is a constant. But actually, mu r is never become constant. Only for simple calculation, we use mu r as constant, just for tutorial. And mu r more look like from the manufacturer measurement because they usually change. That's a BH curve. B and H, the slope between them is the mu r, or the mu. So that's why it never become constant. So most of case, if you're not given, ask you look up from the table, look up from the curve, you can see how much H field, you give you the B field, and then look up. So that's the way to do that. So the question asks us about the flux and the flux density in the air gap, and the inductance for the coil, what's the permeability at 2.5 M. Yeah, so let's go through that. So this is some of the portion we discussed last week, right? I just go through them, make sure you can refresh your memory before I go forward. So the radius, the mean radius, because the inner outer 25 and 20, so mean will be just average, then become 22.5. And then the H field is the Ni, the MMF, divided by the length. So 2 pi r is the magnetic path length. That means this length, right? 2 pi r, this one. So that means the driving force, Ni multiplied the length will be give you 442 ampere per meter. So again, I use A per M. I don't need to use T. T is too inconvenient. So that will be good enough. So according to pH loop, so H field is 442 roughly about in here. We are using this curve, is silicon steel, right? Then the B will be roughly about 1.225. So we look up from the pH loop, another method. If the question give you the mu r, you can use the mu r. It doesn't give them, only give you the pH curve, you can look up from the pH curve. Usually, for particle transformer, we need to look up from the chart. So the area will be pi r squared, because the radius, inner outer radius divided by 2 will give you the radius, and then that's the radius for the core, which is this area. And then the flux equal to B times A. So we got the B parameter here, 1.225 multiplied by the area, give it the flux 2.4 milliweber, right? So the flux linkage again is equal to the flux linking how many number of turns. So that's 250 multiplied by the flux will give you 0.6 Weber. So again, now then we know the flux linkage per unit current will give you the inductance. Really straightforward, just using if you memorize all these equations, all these questions are quite straightforward. Then you get the inductance, 240 mH. So the question then asks, what's the permeability of the core at 2.5? You can see that we especially mentioned 2.5 because the permeability vary with the current or vary with the H field. So in here, you can see that for different H field intensity, you know, H is proportional N time current. So that's why I can see here from the base curve, at B field 1.225, and the H is 442. So this point, 1.225 for B, and H is 442. And then this ratio will give you 0.0277. So that is the permeability. But as I mentioned, we usually use the mu r to represent a magnetic core. So the mu divided by the free space permeability, 4 pi times 10 to the minus 7, give you 2204. So that is the relative permeability for this material. Okay. So that's finished the revision of what we discussed last week. Just refresh your mind. So you can see that for this field section, we just show you how to make use of all these equations. It's a very common equation we use for magnetic. I get in the future, if you take the future course for electromagnetic, I think we do another course. Then after you study this, will be very simple for you. Yeah. You now have a really basic, strong background for electromagnetics. And the next thing to discuss will be how we excite a transformer or excite inductor. You see, all the transformer has a primary coil or secondary coil. We first examine about a coil in the primary side. We use sine wave to excite on the coil to see what happens. We usually consider a sinusoidal excitation. Of course, in the high level, we show you other waveform. But in the lab, I've been asking you if into a sine wave or into triangular wave or square wave, what happens in the transformer, you can try that to see how we want it. But for this syllabus or this section, we only show you about sine wave. But interesting, you can see that the answer for square wave or triangular wave. But anyway, if the basic definition for Faraday's law is, I think everybody know about that in the high school, right? This is the differential of the flux multiplied number of terms will give us the EMF. So if I assume that the voltage input is a sinusoidal waveform like cosine omega t in here, and then this differential equation, we integrate them, you give us the flux value. After that, we can see that the equation for the flux equal to this one. You see, the input voltage, EP, is the peak voltage or the amplitude of the voltage. And then the EP I convert into RMS voltage. Because usually voltage, we use RMS voltage. We seldom use peak voltage. Why is that? Because, for instance, the power voltage here, say 120, that's RMS voltage. So if any voltage we didn't say anything, must be the RMS voltage. That's by common, by law, is RMS voltage. So that's to say in here, EP is the peak voltage, especially mentioned. But I'm going to convert this one to RMS because we usually use RMS for calculation or discussion in same answer of 21.2. Now then, you figure a correlation between voltage, frequency, and most of the flux. So the peak parameter for the flux will be equal to this formulation. And then we just substitute the root 2 over 2 become 4.44. That gives you really famous, well-known equation. You can see this equation everywhere. So that's to say, for a transformer, the voltage, induced voltage, is equal to 4.44 multiplied by the frequency, number of turns, and the peak flux value, the maximum flux. That's the maximum. We like to use maximum because we find that many of the data book, they tend to use the maximum flux value to calculate the core loss, the maximum possible flux. So this again really famous equation to remember. And then sometimes the flux we can replace like B because flux equal to density multiplied by the area. Very common. So sometimes we use this. This is also really famous, more famous than this. So do remember this equation. So some equation I need you to remember. Some question you don't have to. But this is so famous, important equation you need to remember. Day by day, yeah, if you involve anything about electrical engineering. So 4.44 is a really famous parameter. So that is the way we calculate the B field design transformer to see what kind of B field, what kind of voltage. You know, I'll show you how to use it. So for example, like if a transformer is a sinusoidal excitation, 60 Hz, 120 volt, and the primary side has 100 turn, right? Calculate the magnetic flux in the transformer core. So why is important? Because if you excite the transformer with this parameter, this common voltage parameter for a transformer, then from this equation, the 4.44 equation, then you can calculate the magnetic flux density inside the core. That's important because we know this transformer is going to be saturated or not. Would that be the best flux density in the transformer? Or the transformer, we want to excite it with the best magnetic flux. Too low or too high is not good. Okay, so that's why first calculation you see under the excitation, sinusoidal excitation, what is the magnetic flux field in the core? And then what's the current look like? We need to know the current so that we know what kind of wire we use, right? So that's why we need to calculate the primary side current. So the given the magnetic core is 80 centimeters square, the relative permeability is 2500. We usually provide relative permeability. As I mentioned, we don't give you mu, we give you mu R. That's a norm. And the length of the core, 20 centimeters. So that means the length of this core is 20 centimeters. Number of turns different, the area also different. So from here, then we can use the famous equation here, 4.4 for FNAB. So that is to say 120 volt is, you see the voltage we are given with RMS voltage. Divide 4.44, 60 Hz, 100 number of turns, and area 80, and then give us the B field 0.5 Tesla. So do remember the unit for B is Tesla. I think you all know Tesla, right? is the really famous magnetic B field name. And then the H field is H and B are related to the mu. So that means 0.56, we divide by the mu, which is mu naught, I think. So you must memorize the mu naught. Yeah, that's a really famous parameter for the whole double E of physics, 4 pi times 10 to the minus 7. That's a really famous parameter, mu naught. And the mu R is given by the core parameter, which gives you H field 179 amp per meter. So the current is by this H field equation, H field times the length divide number of turns, will give you the current. So now then you can see the current pass through the winding is 0.36 amp, right? So the equation must be also sine wave. So that's the way we can therefore understand a design. So why this equation, this tutorial look really simple, but what we can observe from this tutorial, which is really common design for a magnetic core or transformer. This when we have a core, we do find a number of terms. We know the input voltage, input frequencies. Then from there we can calculate the B field inside the core to check if the core will under saturation or not, or the B field will be suitable. And then we can also get the current pass through the winding. That is the way we calculate transformer, to design transformer. Really simple equation, only one or two single equation, which is this 4.44 equation, and also the H field equation, H times the length divided by N equal to current, right? Only these two equations, you can calculate all the magnetic circuit design. You get that? Any question up to this point? You see, magnetic circuitry is not complicated. Only have a few equations. All the equations are very similar to unsolved. So just try to have clear mind to relate that. Perhaps today or last week is your first few lecture to learn electromagnetic. Right? They're very straightforward. Any question? Go for my tutorial. Press a few buttons in the internet. There's a million of examples. I here just give you some hints, push you to learn a new topic. Any question? Anyway, so let's go through. We have another sort of thing to do. Next thing to look into the ideal transformer. A transformer usually in many textbooks and literature are trying to say ideal transformer. So that means basic if transformer is under good condition, perfect condition, we try to assume the resistance, the winding resistance, the copper resistance will be negligible. And then we say the leakage will be also negligible because sometimes the field supposedly will pass through here, but the field can be some leakage, pass through outside anyway. You never know. So in here, I assume there's low leakage. So if there's a leakage, sometimes there will be some leakage anyway. You never know. And the permeability is really large permeability. That means most of the flux matter will be inside. You see the mu out. Mu out is comparison between the conduction in the air with the magnetic core. If we got mu out really large, we got high ratio of the magnetic flux will go inside the magnetic core compared to air. So that means here, outside is air, here is our core. So we got the mu out here, we got the mu naught here. So that's why we prefer our magnetic core is higher mu out. So that's how we ideal transformer look like. So that means the basic equation for voltage equation, everybody know about that. I think you learned them last year or in high school. So that's a common equation for Faraday's law. The defined dt multiplied by number of turns equal to voltage. Primary, secondary, third side will be the same, but the flux are the same pass through the both primary side and the secondary side. Just make sure you know the primary side we usually refer to here, and the secondary side we refer to the other side, right? So when we put these two equations together, we can therefore V1 over V2 equal N1 over N2. I think everybody knows this equation, right? I just put a symbol N here, make it easier to calculate. So this ratio we call transformer turns ratio. We use turns here because there's a more than 2 turns in here. And the current ratio is an inverse proportion to this, mainly because the power relationship. When we assume the power is E equal, then of course the current ratio will be inverse as related to the voltage ratio, right? So this equation, really basic equation, everybody know about it. So really typical example to show what we're doing. So if ideal transformer connected with resistance 10 ohm and transformer turns ratio N1 over N2 equal to input voltage 120, calculate input current, and output power, right? The basic equation turns ratio is this one. And then in here, we can just using the ratio relationship to calculate the V2 output voltage or secondary side voltage equal to 60. Just simple 120 divided by the turns ratio. And output voltage 60 divided V squared over R give us the power. Output current is V over resistance 6M. Very simple Ohm's law. Yeah? And the input current, just using the current relationship for the transformer, give you 3M. So you just use this really basic equation here. You can get all the transformer parameters. So this is ideal condition. Yeah, really basic. Yeah, I think no ambiguous. And the next thing will be transformer dot location, more interesting. You see a transformer, we have different kind of winding, clockwise and anti-clockwise. You actually affecting the that EMF direction, the induced EMF voltage polarity. So that's why when we have transformer like this, then if I show input voltage positive here, then if you do the winding pattern, means in a way you also have positive polarity here. If you change the clockwise anti-clockwise position, the electric polarity will be changed. These two are isolated, no physical connection. So that's why transformer, the polarity can change. Of course, you can say, oh, AC, they don't have any polarity, but it's phase angle. If it's zero phase angle, this will be zero phase angle. That's what I meant. So that's why the dot rotation is to tell you when we have dot rotation here, we putting a sine wave here, positive polarity here. This will also similar of the same positive polarity with zero phase angle. That's the location of dot rotation. So that in here, we don't care about from this figure, we don't care about the clockwise or anti-clockwise, how to do the winding. Of course, if you look at the winding property here, then you know that how to do the winding, we are able to identify regional stop location. So that means, as again, if you impress 60 Hz in here, 0 degree, this side will have another voltage according to the turns ratio, but also 0 degree at that point. So that's how we understand the dot rotation. So usually all the transformer, we tend to put a dot rotation to represent which one is in phase, which polarity in phase with the primary side. Do you get the point? So now then, if you don't do that, then the phase angle will be confused. You don't know which one is the 0 degree, 180 degree. If you reverse them, then we 180 degree difference. So that's why for AC, it is very important to identify the secondary side, which one will be the dot rotation related to the primary side. But if you secondary side, you only behave as a rectifier, you don't care about the polarity, then you don't have to. But in many cases, especially when we connect a number of transformers together or connect some three-phase transformer, that will be important. So I think in next chapter, we'll try to discuss more about the dot rotation connection. So again, when we say dot rotation appear on one side, this refers to polarity is the same polarity or same phase angle. So that means there won't be 180 volt inversion. Another section, we'd like to tell you about the practical transformer. For practical transformer, then you'll see some leakage magnetic flux. You see when we do the winding here, So there must be some leakage right in here. This is the leakage we don't quite like. But because the magnetic flux, in theory, it will go through the core in here. But sometimes there will be some kind of the string or leakage go to the air. Not that much, only maybe 0 point something %, but still there's something there. So that's a leakage field. So if those leakage field, that means find leakage Li, L mean leakage. Then the basic equation of the leakage inductance also equal to number of turns in here, multiplied by the leakage flux, divided by its own current. That's the definition for inductance, but the flux here is not in the main core flux, but in the leakage flux in the air. So that's leakage inductance. That's the basic definition for the leakage inductance in the primary side. And in the secondary side, when the current pass through, there must be some leakage inductance. That also will be N2 in the N2 number of turns in the secondary side, multiplied by the flux in here, find L2 divided by its current. So that's the basic equation. And then this leakage inductance will behave as a kind of the impedance in series with the winding. So that's why later on we show you how we convert this ideal transformer into an equivalent circuitry. So this one here is the ideal transformer without leakage, without resistance. But the real transformer, we do have the leakage in here. So this leakage is represented by the impedance here. And then we have the resistor that represent this to represent the copper resistance, the winding resistance. Because this kind of resistance is the current pass through the winding. That's why I can have the resistance due to the copper. And then that leakage, the leakage inductance will appear in series as well. So that's how we can see a particle transformer being converted into this kind of the configuration. And then, so that's why we like to sketch a circuitry to represent the leakage component and also resistance component. So that's how we convert them. So we have a resistance in the primary side, the primary winding R1, we also have the leakage component X, L1. In the secondary side, we also have similar component. So that's the two basic components here. And then we also have another new component here. This new component is not easily to represent by the winding calculation, by the leakage calculation, but that is the core losses. You see, when we have magnetic core, the winding putting on the core, firstly, there will be some kind of the core loss. Because for magnetic circuitry, later on we'll show you more about that, there will be some eddy current loss, hysteresis loss. Anything when you use a magnetic core, when we may have magnetic flux pass through a core, there will be losses. So these losses, we can use a resistor in parallel with the core to represent that. And then we also have magnetic flux passing through the core. The magnetic flux also represent a kind of the magnetizing losses due to the flux flowing through the magnetic core inside. So that's to say when we have this flux passing through this circuitry, so this core, this flux, you pass through a lot of the magnetic dipole magnetic material, you cause us the losses. Of course, next week we will show you more detail about what kind of losses that including, as I mentioned, eddy current and also the hysteresis losses. So, so in here we assume we have two components here. One will be the core losses represented by RC1. Another one will be XM. One will represent the magnetizing inductance. So that's all the common well-known parameter in a transformer. So if you go to any material, any textbook or any internet, they will show you this model. So there's many ways to represent this model anyway. Even though in the lab last week or this week, you can also estimate about this parameter. So I think we'll show you how to estimate the parameter in a moment. So you see this transformer, this parameter is in the secondary side. We try to refer this into primary side through the transformer turns ratio conversion. So if we put this parameter in the primary side, easier for us to estimate the component. So that is to say, once we do that, then for the transformer, the turn ratio relationship is N. So that means this voltage in the secondary side, we can therefore refer to the primary side, then we have the even voltage, any primary side voltage, and second side voltage relate to the N. So that means if try to measure the secondary side voltage, then we need to put the E dash 2 here. But once we convert into here, this 2 voltage will be equal anyway. So that's how we refer the voltage from the secondary side to the primary side. And the current as well, the secondary side current, we refer to the primary side become I2 dash. We also have the turns ratio. This is the turns ratio relationship equation I showed you just now. And this is quite straightforward because due to the transformer turns ratio, the voltage equation or current equation of a transformer. And then the impedance we have on that side is we want to refer to the primary side easier for us to calculate. But when we go through the transformer, we find that all this impedance or resistance will have a new parameter relate to the original one and relate to the turns ratio. So which we found that that will be relate to the N squared. So any of the original impedance on the secondary side, when we putting into primary side like this, then we have an N squared in here for the impedance, for the resistance. So the definition why we get N squared, I will show you in later on chapter. But in here, you believe in me any parameter from the secondary side. When we want to refer to the primary side to simplify our calculation, then we found that that's N squared there. And this therefore will be the new equivalent circuitry. You see, this circuitry is quite straightforward for us to measure. So that means if you do any current measurement here, the current look like in series before this component, pair this component. Easier for us to do the measurement. If you use the perfect transformer here, measure from the second side is really inconvenient. So that's why we put everything in the primary side. So that's kind of the equivalent circuitry is also really famous, really commonly being used for all the EE students. So we refer everything to the primary side to make calculation simple. So that means in the lab, if you want to calculate this component, you are refer everything to the primary side, and then we can therefore estimate this parameter. So to estimate parameter, because just now we got series component for the leakage. We got parallel component with the magnetizing or core loss. So now then we got two methods to show you how to do that. One is the open circuit test. Open circuit test, that means you see when the output is open circuit, so the current here will be really small because no current. If there's no current, then all the current will pass through in this kind of magnetizing circuitry. And because the current here is very small, usually the magnetizing current also really, really small compared to the main current. So that is to say, this voltage will be really much close to this voltage. So that means when we know this voltage, we know this current, we can calculate the magnetizing component in here, the RC1 and XM1. That's so-called the open circuitry. So that means when we have open circuitry for a transformer, we just measure the primary side voltage and the current. Using this ratio, we can that's why calculate the magnetizing component RC1. So we can therefore assume this is, although there's some leakage component, we usually assume them to be small and negligible. So this voltage and this current, we can use it to calculate these two components. So just like in the lab, I think last week or this week, if you want to calculate these two components, the magnetic core loss and also magnetizing inductance for the transformer, you just measure the voltage, measure the current, and then you can therefore estimate these two components. So this is called the open circuit test, because we assume there's a no voltage drop in the series component, in the leakage component. That's it. Any question? I think half of the class may have done the lab. So Open circuit test is really common method for testing a transformer. So you refer to my notes, but it's very simple and straightforward. All the internet material should have this. Another one would be short circuit test. So that is to say, if you assume output is have a large current, as large as possible, how to make it large? Short circuit. So in this case, the output will be just like large current. So the short circuit test is just look like this T model. If we try to short circuit in here, then all the current will pass through in here. As I mentioned before, once it's short circuit, this current are much larger than this current. If you short circuit, this voltage will be really small anyway. So the voltage across this component also really small. When voltage is small, of course the current becomes really small. So that's why we use a short circuit test to estimate these four components. This is also a common technique. We try to estimate this component. So if we write the T circuit model into such a way, when we have a short circuit in here, this current will be much larger than this current, and the voltage here will be really small because under short circuit test, we scale with damage the transformer. We only use a few volt, 1 volt, 2 volt, up to 4 volt to excite on the transformer. So that means the voltage across these two components will be really small. The current also really small. Usually this component will be say 120 volt high voltage transformer. Then we only use a few volt. It doesn't have too much current pass through the magnetizing anyway. So now then we can use this voltage, measure this voltage, measure this current to estimate the total resistance and total reluctance. Just V over I equal to reluctance. So we can therefore estimate this winding resistance and the leak gauge impedance. Again, short circuit test, we are showing the parallel component, these two are negligible. Although they are not 100% negligible, but they're small enough. Yes.
Are the losses, what is it? Are the losses? Sorry, I've lost my thought, string of thought. Never mind.
I think you're asking, these losses can be negligible, right? Because we have voltage here, put across this component. Usually transform voltage 10 volt, 100 volt. Now we only using a few volt. So the voltage applied on here much smaller than before. The current here will be really small. So that's why we use this technique. We try to only measure this component, not this component. So that's the name we use for the short circuit test. Short circuit test is really famous test for all the transformer people who measure the leak gauge component, the winding resistance. So that's really common method. So last week or this week, when you go to the transformer lab, then you can do the measurement open circuit and short circuit to measure the magnetizing component and also measure the leak gauge component. So now that it comes to our question, in statement, like to answer. We use the short circuit test to measure this component. Of course, we can therefore using the current and the voltage and the phase angle between them, of course, we can estimate the R and X component. But we can only calculate summation for R1 and R2 dash, or summation for XL and XL2 dash. We cannot distinguish between these two, right? What do you think? So that means we cannot divide or know which one. You can only know the total. You don't know which. That be a problem. That means your left, you can only know the total R1 plus R2 dash. You cannot know one of them.
Well, didn't it not matter because those two were always going to be together?
They're together, yes. When we tell the losses, they're always together. When we primary and secondary current, they always be there. So that's the loss. We only compare the loss anyway, right? So in free way, they're together, don't care so much about it. But in fact, for short circuit test, no other choice. We can only know their total. We cannot divide them unless we take the winding to measure separately. But that's impossible once you have transformer being done. But for good transformer design, these two components are equal. Because primary side resistance, secondary side resistance, these two have curvature relationship. Current relationship. When we design them, this R1 and R2 dash should be equal for good transformer. But for lousy transformer, they are not, right? That's good enough. So even though for these two components, they are equal. So that means that if you calculate the R component, X component is divided by 2, then that would be the R1. Okay.
So we make a good one.
Depends how you make. I mean, you make a good one for me in the lab, right? All the transformers you have. Because you construct your own transformer, right? Or transformer from the company, we have two sets, right? One is the one you do the winding, you do your own winding, you make your own perfect winding for both sides. And then for the commercial one, then they are supplied by the manufacturing. It must be good. You see, this test can just show you a method. Try how to get the short circuit test, open circuit test. Try to get you familiar with the famous test mechanism for transformer. Short circuit test and open circuit test are really famous and well-known method. So you should know how to do it. So that's the way to do it. Okay. So we use assume them to be well designed, they are equal. So just divide by 2, you can get them. So conclusion in here then, to do it, we show you a really basic concept, how to understand the basic parameter for transformer equation. And then we also show you the turn ratio relationship to the voltage. We also show you about the magnetizing component, RX component. We also show you the series connection and short circuit test, open circuit test, right? So this kind of the tests and method are well known anyway. So any of link, I show you a few links here. You can using this link to understand more about the transformer testing and inductance testing. Any question? I usually do upload this to the YouTube, my channel. So you can go through my channel. Later on, I will stop here so that I can record the next one.